All right, welcome. Today, we're tackling one of the deepest, most just absolutely mind-bending mysteries in all of science. We're talking about the quantum measurement problem. And this gets to the very heart of what reality even is. So yeah, let's dive right in.
I want to kick things off with a question that honestly sounds more like philosophy than physics. Does reality actually need an observer to exist? I know, it sounds pretty out there, but trust me, by the end of this, you'll see exactly why physicists have been forced to wrestle with this very question for the better part of a century.
So to even get a grip on this problem, you first have to step into a really weird place, the quantum world. This is the realm where all the common sense rules of our everyday lives just completely fall apart.
And right at the heart of all this weirdness is a concept called superposition. The easiest way to think about it is to just picture a spinning coin. While it's in the air, spinning, is it heads or is it tails? Well, quantum mechanics says it's not one or the other. It's in a state of being both at the same time. It's just a blur of all possibilities happening at once.
And listen, this is not just some neat little analogy. This is what the math, the actual bedrock of quantum physics, tells us is true. On a fundamental level, particles don't exist in one specific spot. They live in this hazy cloud of probabilities, this world of maybes, until something makes them pick a side.
And that brings us right to the heart of our mystery, what I kind of like to call the crime scene of physics. This is the spot where the bizarre but beautiful theory of quantum mechanics seems to crash head-on with the solid, predictable reality that you and I experience every single day.
Okay, so here's the clash. On one side, you have the Schrödinger equation. This is like the master rulebook for the quantum world. And its math is very clear. These superpositions, these maybes, should just keep on evolving smoothly, basically forever. But then, on the other side, you have us. And whenever we actually look at something or measure it, that whole world of maybes vanishes. We only ever see one single definite outcome. The spinning coin lands. The particle is right here, not spread out everywhere. The blur just snaps into sharp focus.
This right here is the measurement problem in a nutshell. What on earth is this process that yanks a particle out of that ghostly state of many possibilities and forces it to collapse into one single concrete reality? What, or maybe even who, is making it choose?
Now, physicists don't have one clean answer, but what they do have are a bunch of competing theories. And for our purposes, let's think of them as a lineup of suspects, each one accused of forcing reality to show its hand.
So, we're going to investigate the three main culprits. First, you've got the old-school classic, the Copenhagen interpretation. Then there's the wild, almost sci-fi idea of many worlds. And finally, a totally different angle called objective collapse theories.
All right, time to put on our detective hats. Let's start interrogating these suspects one by one and see if their stories actually hold up under pressure.
First up, the oldest and probably most famous suspect, the Copenhagen interpretation. This was the view of quantum pioneers like Niels Bohr, and its explanation is, well, deceptively simple. It says that the very act of measurement, the act of us observing, is what forces the universe to pick a card. The maybe becomes an is, simply because we looked.
But this is where the story starts to fall apart. What in the world is an observer? Does it have to be a conscious person, a scientist in a lab coat? Could a camera do it? And what about Schrödinger's famous cat? Is it really both dead and alive until a person opens the box to look? Copenhagen, well, it just kind of shrugs. It doesn't give a clear definition. And that leaves this massive, glaring hole in the whole theory.
Okay, let's move on to our next suspect, who takes a completely different and, honestly, a much wilder approach. The many worlds interpretation basically says, what crime? There was no crime. The wave function, that blur of possibilities, never collapses at all. It never goes away.
So you've got to be asking, where do all those other maybes go? And well, this is where your brain might start to melt a little bit. According to this theory, every single time a quantum choice is made, the entire universe splits. In our universe, the coin lands on heads. But in another, brand new, parallel universe, it lands on tails. Every single possible outcome becomes real, somewhere.
The biggest problem for many worlds is, well, the sheer number of many worlds. I mean, it's an incredibly extravagant idea. If these other universes are real, where are they? Why can't we see them? And why are we stuck in this particular one? It sort of solves the collapse problem, but it does so by creating a whole new set of seemingly impossible questions.
Our final suspect tries to find some middle ground. Objective collapse theories say yes, the collapse is a real, physical thing that actually happens. But, and this is the key part, it has absolutely nothing to do with us, or observers, or consciousness. Instead, it's just a fundamental, built-in feature of the universe, maybe a new law of physics we haven't found yet. Superpositions just randomly and spontaneously collapse all on their own.
The trouble here is we've got no proof. Zero. This idea requires us to actually change the Schrödinger equation, which is one of the most successful and well-tested equations in the history of science. You have to add new, unproven rules to make it work. So the question becomes, why would nature have this weird, random collapse rule, and why is it so subtle that we've never, ever been able to detect it?
Now, I have to mention a really important clue in this whole mystery. It's a process called decoherence. Basically, it's what happens when a quantum particle bumps into its environment. You know, air molecules, light particles, whatever. All that interaction scrambles its quantumness. It explains why we don't see big things like cats being both dead and alive. But, and this is crucial, it only explains the appearance of a collapse. It doesn't explain why we experience one single outcome and not another. It smudges all the fingerprints at the crime scene, but it doesn't tell us who the culprit is.
So, after lining up all the suspects, where does that leave us? Well, the truth is, the case is as cold as ever. We've interrogated the main theories, and we find ourselves without a clear confession. The case remains wide open, and frankly, the implications of that are just staggering.
And look, this is why this whole thing matters so much. This isn't just some abstract puzzle for a chalkboard. The answer could completely rewrite our understanding of everything, from the nature of consciousness itself and how our brains work, all the way up to the flow of time and the origin of the entire cosmos. The answer is tied up in solving this one mystery.
Think about that. For nearly a century, the smartest minds on the planet have been fiercely debating this, and we still have no consensus. We live in a world that is fundamentally quantum, yet we have no idea what that really means for the nature of our own reality. We are still explorers at the very edge of the map.
So I'll leave you with maybe the deepest question of all. At its core, is the universe a grand cosmic lottery where everything happens based on pure random chance? Or is there some hidden deterministic clockwork underneath it all that we just haven't been able to see yet? The answer to the measurement problem could very well be the answer to that. And that, for now, remains unsolved.